In this video, we will do an optimization problem where we minimize cost. So the example says a cylindrical can is made out of two types of material. The top and bottom cost $5 per square inch, and the lateral surface costs $2 per square inch. If the volume of the can must be 12 inches cubed, or cubic inches, find the dimensions of the can that minimize its cost. So this is a very typical optimization problem that actual manufacturers deal with. They want to find the cheapest possible container or packaging for whatever product that they're distributing. Okay, so I want to first give you 4 minutes to try it. So pause the video in 4, 3, 2, 1, pause it and try it for about 4 minutes. It's likely not going to be enough time to finish the entire problem, but hopefully it's going to be enough to start it off and think about the key ideas. Alrighty, so hopefully you did that. Hopefully you paused it and tried it for about 4 minutes. Let's talk about it together now. Okay, so I want to begin by identifying the quantity I am trying to optimize, that I want to minimize or maximize. And in this problem, that's the cost. So I want to minimize the cost. That is step 1. Identify the thing that we want to minimize or maximize. Here it's the cost. Step 2 is we draw a picture, if it's applicable. And in this problem, I would say it is. We have the cylinder. So I'm going to draw a cylinder. Okay, so we have that top circle, we have these sides. Then we have the bottom. Draw a dashed line for the way the circle curves around in the back. Okay, and I'm going to assign some variables. So we can have the radius. We can have this height. All right, and the problem tells me that the top and the bottom are supposed to be $5 per square inch. Okay, whereas the lateral surface is $2 per square inch. Okay, so we are on to our next step, which is to write down our objective equation. So remember, our objective is just an equation for the quantity that we want to maximize or that we want to minimize. In this problem, that's the cost. So I'm going to call it C for cost. So the cost of this thing, to be able to find it, I need to know the area of the top and of the bottom and of this lateral surface. So the lateral surface, I should have mentioned before, is the surface on the side of the cylinder. So to get that, I would take 5 times the area of the top plus the area of the bottom, because both the top and the bottom will cost $5 per every square inch. And then it's going to be plus 2 times the area of that lateral surface. Okay, now let's evaluate this. So I'm going to have to remember some formulas from geometry. So the top and the bottom are circles. So their areas, in fact, they have a circle of the same radius. So they're both will have area pi r squared. So this is pi r squared, and the area of the bottom is pi r squared. And for the lateral surface area, the way I get that lateral surface area is I have to find the length all the way around. So the length all the way around the circle, and that circumference is 2 pi r. And then I multiply that by the height. And the way I can think about that is if I had a cylinder, imagine I had a sheet of paper that I rolled up into a cylinder like this. If I were to sort of cut it, if I were to sort of cut this cylinder here and then unravel it, it would make a rectangle. And this length up here is the circumference of that circle. And then this length is the height. So when I multiply the circumference times the height, that will give me that lateral surface area. So the circumference is 2 pi r, and I have to multiply that by this height, h, and that's my lateral surface area. Okay, so if I simplify, we get cost equals, this is going to be 10 pi r squared, because in parentheses this is 2 pi r squared. And then when I multiply these 2's, we get 4 pi r h. So that's my objective. Right now it's in terms of 2 variables. I need to get it in terms of 1. So to do that, we need a constraint. So the constraint is another equation I get using info in the problem. So the problem also tells me the volume of this can has to be 12. So if I use the fact that the volume is 12, remember the formula for the volume of a cylinder, it's the area of the base, which is pi r squared, times the height. So times h. So that needs to be equal to 12. So once we have our constraint, I isolate one of these variables so I can substitute into the objective. Typically, I isolate whichever variable is easier to isolate. And I would say h is going to be easier. If I divide pi r squared, we get 12 over pi r squared. If I were to isolate the r, we'd get a square root, and overall that's a little bit more complicated than this, which is why I'm isolating h. So now we are ready. We are ready to substitute. All right, so if I write my objective equation, so that was c equals 10 pi r squared plus 4 pi r times h. And now let's plug in our value of h, which is 12 over pi r squared. Let's first simplify this. So c equals 10 pi r squared. And I could cancel a pi. I could cancel an r, and I'd be left with an r on the bottom. So overall, 4 times 12 gives me 48. So we get 48 over r here. Okay, so our cost function is pretty simplified. Now we are ready to take the derivative to find critical numbers. Okay, so in this case, the variable is an r. So we're going to take ddr of both sides. All right, so on the left-hand side, that gives me a derivative, which I can write as c prime. I could also write it as dc dr if I wanted to. So a derivative of c. On the right, we just take the derivative of this normally. So I'll get 20 pi r first. And for the derivative of 48r, remember, we can think of this as 48r to the negative 1. And if I did the derivative of that using power rule and simplified it, it would give me negative 48r to the negative 2, which I'll bring to the bottom and make it r squared. Okay, so I'm going to need to figure out when is this 0 and when is it undefined. So let's get a common denominator. All right, so I would have to multiply this first term by r squared over r squared. If I do that, on the numerator, I will get 20 pi r to the third. And let me just subtract the 48. Let's just combine the fractions. And the denominator is now r squared. Okay, so when is this derivative equal to 0? It'll be 0 when? I need the numerator to be 0 to make this whole fraction be 0. So that happens when 20 pi r cubed equals 48. So if we rearrange this, we get r cubed equals 48 divided by 20 pi. And I could cancel a 4 from the top and the bottom to leave myself with 12 over 5 pi. And if I cube root both sides, we get r equals the cube root of 12 over 5 pi. All right, so that's when the derivative equals 0. I also need when the derivative is undefined. So it's going to be undefined when the bottom is 0. So that happens when r equals 0. But that's actually impossible here, because this would make, if the radius of my cylinder was 0, that would make the volume be 0, which can't happen because the problem told me it's not supposed to happen. The problem told me what the volume was. It told us the volume is 12. So because of that, it's impossible to have the radius be 0. So which can't happen, so we ignore this. So we ignore r equals 0. All right, so now we have our critical numbers. It's the cube root of 12 over 5 pi. We need to now test them. Test the critical numbers. So there are 3 methods that we've talked about for doing that, for testing the critical numbers. Okay, so there was the closed interval method. There was the first derivative test plus a little bit of justification. There's also the second derivative test plus a little bit of justification. Okay, in this problem, because r is not allowed to be equal to 0, if I were to think about the interval for r, it's actually open parentheses at 0, because it can't be 0. That would make the volume be 0, which is not allowed, onwards to infinity. I could technically make the radius be as big as we want. If the radius became huge, though, it would just mean that the height gets super, super small to make the volume stay 12. But this is an open interval, let me just put a bubble around this. This is an open interval, so I couldn't even use the closed interval method. You could only do it on a closed interval. So that leaves us with either the first derivative test or the second derivative test. And with this function, I think the second derivative is going to be pretty simple actually, because for the 20 pi r, when I do the derivative, that'll just become a nice constant. Okay, so I'm going to do this. We call this method 3, using the second derivative test, plus a little justification. Because the second derivative test is a test for local mins and local maxes. But in these optimization questions, we're trying to find an absolute min or max. So that's where the justification will come in. Okay, so we got to begin by taking our second derivative. So the derivative of 20 pi r is 20 pi. The derivative of minus 48 over r squared is going to be plus 96 over r to the third, if we work it out. Okay, so what we hope when we do these optimization questions and we test it using the second derivative test is that our second derivative is either always positive or always negative. And when I look at this, I know 20 over pi, that's always positive. And the 96 over r to the third, that's always going to be positive since we know r, the radius, is greater than 0. So as a result, this whole second derivative is greater than 0 for all values of r. So our function, the original cost function, is going to be concave up the whole way. So here's where our justification comes in. Since c double prime is greater than 0 for all values of r, the local min at what our number was, r equals the cube root of 12 over 5 pi, is, let me draw a picture just so we can justify it before we state it. So we'll have this cube root of 12 over 5 pi, and because our second derivative is positive, my graph is going to be concave up. And it's going to be concave up the whole way. So it's going to stay concave up the whole way. So that means at this local min, I know it's a local min by the second derivative test, that has to also be an absolute min. So this is also an, whoops, this is also an absolute min. All right, so we're not quite done. The last thing I got to do is make sure I answer what the question wanted in the first place. So the question said to find the dimensions of the can that minimize the cost. So I need the dimensions, which means the r value and the h value. And we know one of those. We know the r value. It's this cube root of 12 over 5 pi. So for the dimensions now, let's start to write them. We just said we know the r value. R is the cube root of 12 over 5 pi, and the units of length on this problem were inches. And to get the height, we had this equation for h. It was 12 over pi r squared. So if we plug in our value of r, we get 12 over pi. And then if I think of this cube root as being a 1/3 power, if I square that, if I square this value of r, the exponents will multiply. So we'll get this whole thing being raised to the 2/3 power. So it's the 12 over 5 pi being raised to the 2/3. And units again are in inches. So this is my r, my radius, and this is my height. Those are my dimensions. All right, so in terms of our goals for this section, we've completed our goal, which is to recognize and solve optimization questions. So as you've seen over these last few videos, optimization problems can be challenging. There are a lot of steps to them. Part of what makes it challenging is that they often involve word problems, which we got to interpret in terms of math. And then we got to do a derivative, and we got to test to see whether we have a min or a max. So there are a lot of steps to them. And like with the related rates, there are just a lot of different scenarios we could encounter. We did one example where we maximized or minimized a sum. We maximized an area of a rectangle. We had an example with a cylinder in this video. So there are a lot of different shapes that we could see. So it's a topic where it just takes a lot of practice, seeing different scenarios and getting more comfortable recognizing when to use which technique.